blur part, you can try this exercise. This exercise is given here. I suggest you try this question before you go for the exam, because if you are able to do this, I think in the exam you should be able to find. In exam, there's one full question on GPA. Try this exercise, should be fine. Look image is basically just teaching you how to use OpenCV. Look image and display on the screen. This is the first exercise. If you want to learn how to set up your computer, just look at this. This one is I did this exercise before, right? Addition.
你有看过吗？有，它是因为 WhatsApp 的关系，和 WhatsApp 的是一样的，因为你 send 给我，然后我拿下来啊，但是现在这两看是一样的，就是我 screen 出来是不一样的。
Use this as your initial
做
point.
个人可以像还是一样99%，99.8%。
It shows to you how to allocate memory.
我昨天改了5个小时，6个小时，然后我最后是放回去原本。
This is not
就讲我6个小时给你改没有东西，没有，最多就是8。
so we use this. I'll show you how to compute more efficiently. Basically, you can use this equation as well. It's not so efficient. More efficient means you use extra memory. You might use extra, but then you launch the kernel by passing the bit size or size and the parameter. So it depends on the whatever arguments that you have there. Okay. And once you finish, you copy back the memory from device to host, and then you free the memory. Okay. So once you copy it back to host memory, the caller will have the data. Okay. So when you call this function here, the data will be inside C. So you start bring the C and V and answer. Okay. So this is pretty basic. The most important part is how to set up before you call and how to copy the data. Okay. This one is important, and this also will come in the exam. Okay. So you need to know how to do this. Okay. Another thing is how to compute this grid size. Different problem, different way of computing. Actually, it's the same. It's the same depending on the size of this track size. So track size is 500. Okay, in example, I give you a different value. Okay, you just plug it here, but you need to understand how this come about first before you're able to write the proper grid size. Okay, if you want to try this exercise, each way is inside. So go to the next exercise. This one. This one is a grayscale, which we discussed last week. Just that you need to modify the code because the code that is given is not correct order. Okay, because OpenCV, in fact, not just OpenCV, the graphic cards also use this same format as well. The blue comes first, the green comes later, the red comes later. So it is in this format. So this is the low address. Higher address is going this direction. Low address is here, higher address. So the low address, that means if I say this index 0, this index 1 index 2, okay, or you from this side you'll be 0. Okay, so the higher address store the rate, the lower address store the level. Okay, but the code that is given here, if you copy unchanged, it will not work because if you copy this directly, this one actually before this class, right? It assumes that rate is at 0. Rate is here. Green is correct. Okay, and the blue is here. But for OpenCV and also for the GPU, sorry, not GPU, the graphic cards will assume blue is at the lower address, so you have to change them. Okay, So you can try this code here to convert the color. Okay, so you try to do it here. Okay, here. This is a panel to grayscale, and then fill in the blank there, fill in the blank here, fill in the blank there. Okay, fill in the blank here. Actually, it's quite obvious. It's grid size and block size. And I already passed in the parameter correctly here. Then copy it back. Remember to copy. If you don't copy, you will not be able to display. You copy it back to the memory, and free the memory. Then this is called by a function right over here. Called by this function here. So you return and then return the up image. And this up image is the one that is a grayscale image, which it will be shown here. Okay, so I use this OpenCV. Actually, this is a notebook. This notebook OpenCV CV image. The actual one is CV2.image, but because I cannot use this in notebook, so I have to use my own one. This is my own one. I can name it like this. Behind the scene, you actually on the cell, inside the cell. Okay, so that is for, you must try this before you go for the exam. Okay, because this one will help you a lot in order to understand, write the proper code then. Okay, it might be different. Okay, different code, but basically they are all the same. For example, here the track block size is 32, so I ask you to use 32 for X and Y. Okay, so you have to compute block dimension for X and Y. Okay, this one is the Z, you just need one. Okay, the grid size, there are two parameters. In the previous exercise, you see only one because it's one dimension. Now it's two dimension, X and Y. Okay, so you have to compute both. But luckily, the formula is the same. So you refer to the X, you should be able to do the following. So this X, Y, Z. Okay, the grid size, there's no Z, there's only X and Y. Sorry, there is Z as well, but we don't use it here. Okay, here error because I did not do anything. So by right, when everything is done properly, you should see the proper image. Okay, there are two images. You can add elephant there. Now rows, whatever that you downloaded, you can actually put at the back. It will process that. Okay, in assignment, I prefer you to, actually you should because you don't have time, 15 minutes only. So if I ask you to change the image, I'll give you the image. You should be able to take the image, put in the file name there, okay, and then run the program again. I don't expect you to go into the code, change here and then asking your friend what's happening and run. Because you have to change the code once you enter the code, there will be error.
我 try 过很多，可是错误的
You'll be wasting time.
我 try 过300多 ，try 过300跟400。
Okay, this one is blur image. Is this part here?
400倍，可是它的不是错的。
So blur image. There is some code there as well, but I'm not sure whether this code is correct. But even though it's correct, you have to make some changes as well, because the variable that I use is different. Let's see. The image. This one is more complex, but I give you the code for the
名方还有
single thread
image filter
CPU.
image filter，
Single thread CPU code is here. You can start from here. You can
面也
copy
有
this.
直接在那边就
Start from here and then do some adjustment to the code. Okay, I have the code. This is working code for the CPU. Okay, this one is for the CPU. For GPU is blank. This one CPU is blank. GPU is not there. This one. I think it's around. Yeah. You have to put in here. Okay. First you compute the X and Y, and then the code. I suggest you refer to my one rather than this because my one is working. You can also refer to this. I'm not sure whether it works or not. This one. Okay, because I use different variables, so you have to go and figure out what to change there in order to fix it. In fact, I also based on this computation here to write the code. Okay, so my code is a bit lengthy for the single core. Maybe, I'm not sure this one is complete, now you better check it. But I think it's more or less complete. You can try this. The most important thing is you understand what is going on, not just copy and paste. Okay? It's the same thing when I base on this code, I have to understand first. Then only I wrote this code. Yeah. Okay, so I have to understand the code before I write this. Otherwise, I will not be able to come up with this solution, right? Sorry. It's not as grayscale. Should be looking at this one. Alright. So it's a bit lengthier than just now. So I think it's based on this better. Because I already put nicely the blue first, green, and then red. Okay? But take note, this one is for a single thread, a CPU. So you have to make some changes there. Oh, sorry. Let's go back to this. So I already explained that. Now we move on to the next part, which is how do we know whether we can parallelize the code or not? Okay, so we have to look at some condition first. This one is described by Bernstein a very long time ago. And it's still applicable today. Actually, when he described this, it's not for pair computing, it's for something else. But we can use it for pair computing. First thing is the classification. I think I already explained the classification before. Right? At the program level, job level, task level, and then down below is program level, and then to arithmetic level, and then finally to bit level. Right? So that is a classification where is a part where you can parallelize. Okay? So some part you can parallelize immediately at the processor level or the bit level. But normally we already done this. Actually bit level we done it in our single instruction, single data level. Okay? Because bit level our data is 8-bit, right? So we can process it immediately in one operation. Okay, so this one available in all computer even. Now arithmetic logic unit normally is those which has multiple data, single instruction multiple data, SIMD. In older Intel, it is known as MMX, and then it's known as SSE, and then later on they call it AVX, AVX35, 556, and then AVX 512. These are latest one. Okay? The size, this size here is the number of bits. So how many bytes? 16 bytes. So you can process 16 bytes in one instruction, in one go. Okay? So this is at processor level, the one that at the top here. Okay, processor level, you can perform this. Okay, so your Intel processor can do parallel computing as well at processor level. Okay, next we want to find out whether we can parallelize now, because even though we have the power to do so, we have to look at the statement whether there is any dependency. If there's dependency, we know that it's a big problem. The first thing is we have to identify whether it can parallelize. Okay. Second thing is if we find out that it cannot be parallelized because there's dependency, we have to find out whether it's truly cannot be parallelized. So we want to find out whether it's a true dependent or false dependent. Okay? True dependency or false dependency. Because sometimes it looks like it is dependent on one another, but actually it's not. So that is false dependency. Okay, so basically I explained everything here. I'll skip that. Okay, so we have to first look at the code first and analyze. For example, in this code here, this code is written for single instruction, multiple data without this support, without the processor support. We have single instruction, single data. Okay, Intel also support this using this technology, the old version, the latest one. This one no more use. You can use still, nobody uses it anymore. Okay, all Intel, I believe, support this. all x64 support this, starting from here, support this. Okay? Only later generations will support this. You have to look at the processor. Processor, different support. So you have to see whether they exist. Okay, suppose this is supported, let's say this one. We can process 16 bytes at one go. Okay? So we have single instruction, single data. We also have single instruction, multiple data in our Intel. Okay? Then we can improve this. This one actually handled using this technique. That means byte by byte. We look at byte by byte or single element at a time. If you want to configure it to run in parallel using our single instruction, multiple data from Intel. This one without multiple core, single core. Okay, one core. One core has this single instruction, multiple data. So you can do some parallelism in single core even. Okay? Normally what we did in our OMP and MPI. Okay, we did in our MPI. Can you hear me? Testing. Shit, we don't have that. Okay, can you hear me now? So you can transform this into different order. Testing? No. Okay. We go here. Testing. Can you hear? Yes, I can hear what they say. Okay, so we have this, which is run in single instruction, single data. We want to convert it into one or single instruction, multiple data. So single instruction, multiple data, and we have this code here. Actually, this one means you go from 1 and 1, and then every time you move, you increase by 64. Yeah, it means that. Yeah, so if you look at this, actually it's the same as what we see before. I equals to 0, and I equals to 1. I less than 10, I plus equals 64. It means that. Okay? What you see there, I dot 64 dot n. Okay? That is basically this in C language. This one is in a different format. It is in Python. In Python we write this. Okay, so what it means is you use 64. Here is 16. Actually we don't have 64 in Python. Let's change to 16. 16. So you process 16 at one go. You process 116 and then you move on to the next 16. That means this one is actually 16 bytes. 16 bytes. Okay? And you process in one go. Okay? So what it means is this: you multiply, right? Multiply with A. There's A here. So normally what you do is you multiply. Take this, you multiply, and then you get the answer. The answer is placed. Then you move on, you multiply this, another answer. Multiply this, another answer. So how many times? Let's say there are 16 bytes altogether. If you do one by one, then it will be 16 cycles. Okay, you have to do one by one. But if you use single instruction multiple data, basically you're multiplying also. But you multiply this independently in one instruction. So when you multiply this. So in one cycle. That is a single instruction multiple data because you got multiple data. Okay, so you can use AVX 412. Okay, this AVX 412 is a technology name. the register, you learn what do you call AX, BX, CX, right? In Intel x86, isn't it? You learn this register, right? But here you have extra register. On top of this, you have another register. It's called YMM. Sorry, ZMM. 0, ZMM1, and so on and so forth. Okay, until they are really two altogether. And the size here is this size. Okay, it's very big. Okay, normally we are talking about here is only 16 bit, right? Here is 412 bits. Okay, it exists in our modern computer. The computer, maybe your computer also has it. Okay, you can do cloud computing, single instruction multiple data in single core. So if you have multiple core, you can do this even more. Okay? So this is at processor level. Okay, just now I was talking about what we have, and we haven't gone into the condition yet. Now, what is the condition to find out if we can do cloud computing? Can you hear me at the back? At the back? This side, can you hear me? Yeah, I cannot hear myself, so I don't know whether you can hear. Okay, there are three conditions. The first condition is in each iteration, the iteration or the statement it does not write in the location that is read by the other instruction. So iteration here actually it means the loop. You have a loop, right? You have a for loop, and this for loop will run this code multiple times, isn't it? But if you break it open, so you break it open, you can see it run. Right? So this is the first cycle, first loop, second cycle, second loop, third cycle, and so on and so forth. There's a for loop, right? You can break it down like this. Now, what you do is you don't run them in loop, but you assign them to the different core. Let's say core number 1, core number 0, run this. Core number 1, run this. Core number 2, run this. So you break open this for loop into this. And that's what we do normally, right? So we assign thread. In our case, we call thread 0, thread 1, thread 2. Okay? So iteration here means this iteration. So this is the first iteration. This is the second iteration. Okay. So what it says here is this: iteration 1 does not write into location that is read by iteration 2. So this iteration here, you write into data that is used here. Okay. Your code here write into the data that is used by this second iteration. Okay. So that is the first condition. If you have this, then you cannot do computing for this code here. For this code here, you cannot do computing. If it does not, then possibly can. Okay? You have to look at the second condition. Now the second condition is iteration 2 does not write into location that is read by iteration 1. It's the reverse. This iteration, okay, it does not write into the location that is written by it or used. Okay, this one is right. This is read by this iteration. Okay, so this iteration does not write into the location where this second iteration is reading. Okay, the same thing. You cannot go this way as well. If this is writing into the data that is used or read by this iteration, then it will fail as well. Okay. And the last one is it does not write into location where it is written. That means this guy does not write into here, while this guy also writing. Okay. And this guy is not writing into the location where this cycle also writing. Okay. So the last one is write. Okay. The first two is read write. Okay. Write into some location where it's read by another iteration. Okay. So if you don't have all this then you know that you can parallelize the code. Okay, if you have this problem, then most probably you cannot parallelize. Most probably because we will discuss later, there is false dependency and true dependency. So we have to analyze still, check whether is it real dependency or not. Okay? But basically this is the condition that we must obey. And we will see some example later, how to identify which part we can parallelize and which part we can't. Okay, now I want to discuss whether this is real dependency or false dependency. Okay. On the left hand side is flow dependency. On the right hand side there's no dependency. Okay, let's look at this flow dependency. Flow dependency means true dependency. Okay, you see I use C, find the solution from A and B. So you take A multiplied by B and you put the value into C here, right? And then this C is used to find D. So isn't that dependent on one another? So this is flow dependency because it's a flow and it depends on the previous code or future code. So in this case here in the previous code. So you have to do this one first before you do this. Right? You cannot do this instruction first before you do this. Alright. Because if you compute this D, your C is not initialized with the proper value. So you cannot do the second instruction first. You have to do the first one, which is basically logical. But then if you run that in parallel, how are you going to ensure that they run in the sequence that I mentioned? For example, if I let track 0 run this, track 1 run. When they run at their speed, isn't it? So they're not going to wait for one another. If let's say track 0 run first, then track 1 run this, then it's okay. But if track 1 run first, that means this one run first, then it will be wrong. Right? So if you parallelize this code, you will not run for one. Okay, let's look at no dependency. No dependency, if you look at this code, C relies on A and B. D relies on 2D, but this B is not changed, right? Previously it doesn't change, come from outside. Okay, it doesn't change. And how about E? It depends on A and B, but A and B is not changed. So this A and B come from outside. So can you run this in parallel? Yes, you can run that in parallel because they are not dependent on one another. They can run in any order, it's still correct. The solution is always the same. Here the solution is different if the track run in different order. Here the solution is all the same, even though they run in different order. So this is no dependency, that is flow dependency. Okay, flow dependency here is actually true dependency. And there are some not true dependency. So at the top there, this is a flow dependency or nothing, right? It's true dependency. True dependency means is exactly this dependency, and you cannot change it. Okay, is real dependency. Okay. The other one is anti-dependence, output dependence, and there is also input dependence. But input dependence is not written here because it's actually not important. Okay? Only this tree that is important, that's why it's here. Okay. How do we write it first? If we want to write dependency, there's a notation. S1, S2 is a statement. Just now I was talking about iteration. They are kind of related, but it is different, slightly different. But Bernstein condition still applies. Just now I was talking about cycle, right? So this is one cycle, this is one cycle. Inside here, there is code. Right? So you got statement inside there. Statement 1, statement 2, statement 3, statement 4. Okay? So this statement can depend on one another. Just now I was talking about the dependency between iteration. This one is inside the iteration itself. Here we are talking about the dependency inside the iteration. This iteration. Right? So you got S1. This one basically is statement number 1.
statement of okay, of course we have multiple statements, but let's look at two statements first. Okay, if it is true dependency, okay, true dependency between S1 and S2 means S1 write into the location read that is later read by S2. Okay, so statement 1, example, just now, A, B, next statement 2, let's say this one is Z, is C plus 1. Okay, so the way we write is, this depends on S2, so we write S1, T, we write T here, the top of it, right, and then S2. Okay? So we write S1 has a full dependency or true dependency on S2. Okay? And the example for this is this one. Okay, you can see it on the example at the bottom there. It says S1 and S2 is two different statements. S1 writes into a location, later is read. So this write into this location, later read. So this one start first, this one start later. Okay? So S1 has two dependency or full dependency to S2. Okay? Yeah, the other dependency, this one also dependency. If you don't fix it, it's dependency. Okay? And if you run in parallel, your code will break. Okay? This is called anti-dependency. What is anti-dependency? So this is true dependency. Okay? Anti-dependency. Okay, you write S1, A stands for this anti-dependency. Yes? Maybe I use this example better. So anti-dependency is between S1 and S2, which is means that S1 read from location later written by S2. Okay, so S1, yeah, just use this example better. S1, yeah. Okay, don't look at S0. We are looking at S1 and S2. This one assume that it's already S2. So B is read here, and then it's overwritten later. Okay? Just now it's different. Just now is you write and then you use later. This one is you read now, you write later. Okay? You read now, and then you write later. Okay? Is the reverse. So this anti-dependency. Yeah, you just go down there, example. That's one. Using that A. Then S2 is B. You override. Okay? So you read and then you write later. Okay, this one is write, you read later. Okay? Okay, this anti-dependency is dependent, right? For example, if I were to run this by one thread and run this by one thread, if this one run first, then this one run later, it will be okay. If this one run first, and this one run later, it will be not okay, right? Because if this one run first, it will override the B. Right? If this one run later, you use the B that is written later. Okay? That means it's corrupted already. Right? So anti-dependency is actually bad. You cannot run in parallel. But this is actually false dependency. It's not written there. I think it's written down below. False dependency. What does it mean? It means it's not real. Okay? It's not real dependency. If you run like this in parallel without any change, then it will break. You have to modify it slightly. You can modify it so that it becomes no dependency. Okay, false dependency means we can change the code. It will still work properly, but it will not break. So we can save this. Okay, this one we cannot save. It's true dependency, we cannot do anything because it's real dependency. This one is a false dependency. You can save this. I'll show you later how to do that. Let's look at the output dependency first. Because this output dependency also has the same characteristic. So output dependency, there's a mistake here. I think I can modify this. This one is not I, this one is O. This should be written like this. There's a mistake here. S1, O, S2. This is how we write it. How do I know it's O? Because the output dependence O here. Okay, true dependence T. Okay. NT dependence K. Okay. So I is input dependence. But input dependence we don't discuss here because input dependence actually it means no dependency. Input dependence actually is no dependency. It's actually read. Read, there's no problem there. So you can run them in parallel. So we don't discuss it. Okay. So this output dependency it means an input dependence between S1 and S2 that S1 and S2 is reading, sorry, not reading, actually it is writing into the same code. Actually here is also wrong. Writing to the same location. I think I know why. Actually it's trying to say this is input dependence. So input dependence is correct. I can see that it's input dependent. So this one is not output dependent, and this one is wrong. This one should be input dependent. Output dependent, the right here. That one is wrong. That one is input dependent. It's O. Okay, and here you should change to this. And output dependence between S1 and S2, S1 and S2 means that S1 and S2 are right to the same location. Right to the same location. You don't delete that because that one is actually correct. You just change it. You have a note there. Just change it. This is input dependence. Leave it like that. And then the output dependence you write down at the bottom. Output dependence. This is the notation. This is the O. And then this is the description. And output dependence between S1 and S2 means that S1 and S2 write. That one is read. This one is write. Okay. Now we don't discuss input dependence because input dependence is read. As I said before, we don't have any problem if we run in parallel, we can run in parallel, right? So we exclude that from here because there's no dependency involved when we read. Now when you write, okay, S1 write into the variable where S2 also write, then you have dependency. But really this dependency is also false dependency. We can change this code here slightly in order to make it not dependent. Okay. So this true dependent we cannot change. This false dependent we can change the code to make it non-dependent. Okay, this also we can change to make it non-dependent. Okay, once again, anti-dependence is false dependency. If we don't change, it is dependent. That means it cannot run in parallel in pure form like this. You will break. We have to change this code so that it does not break. Okay, the same thing here. If we don't change the code, because there's a code down below there. Let's see. Okay, here's one example. Example here. That's one. You write B, let's say 38 here, and then you write again. The second one you write already, and then you write again. Okay, any number here, let's say 2. Okay? So you write and then you write. Okay, here if you run in parallel without any change, you'll break it because it's incorrect. Okay, you cannot run them in parallel. Okay, if you want to run in parallel, you can. But you have to break. You have to modify. But before we see how we can modify it, let's look at another name that we normally use for this. Just now I was talking about right, read, right? Actually, we can use that name. Okay, for true dependency, true dependency is read, read after write. So we can call this read after write. Okay? For anti-dependence, there's another name for it. We call it write after read. Okay? This is read after write. Okay? This one is write after read. So write after read. Okay? Write after read. This one is read after write. Okay? Okay, how about output dependence? Output dependence is write after write. We're looking at this. Write after write. Write after write on this A. This A is write after write. This is read after write. And this one is write after read. And this one is write after write. Okay, write after write. Okay, just now I mentioned to you these are false dependence, right? So read after write and write after write, they are false dependency. So how do we fix it? Okay, you can use that example. Maybe I use this example better. Okay, what I can do is, actually it's quite simple. If you look at this example here, of course there's some other program below there. Maybe I'll write somewhere, somewhere here, so that we can better appreciate it. Okay, suppose here is the code B equals extend from here, right after it. Let's say this is 38. Any number. Okay, and then we have, let's say this is statement 0, statement 1. This one is say A equals to B minus 38. Okay, x2 is B minus 1. Okay, and then let's say here is S3. We use this B. Okay, that's it. I got 4 statements. But I'm just interested in these 2 statements. I want to see whether these 2 statements can be run in parallel. I don't worry about this. I worry about this first. I want to see this. Can it be run in parallel? And I find out that this is anti-dependence because it's right after read, which is this one. Right after the anti-dependence. Right after read. Okay, so I know that I cannot run in parallel. So how do I fix this? Luckily the solution is simple. I just change this name. Okay. Let's call it B0. Call this B0. Because I changed this B0, I have to change this to B0 as well. I just rename. So the solution is renaming. Renaming variable. Effective variable. Okay, this is a solution. The solution is renaming the affected variable. The affected variable is B, right? So I just rename one and I can choose. If I choose this B0, okay, if I choose this B0, then I have to put this B0. Okay, change this. If I want to change this, then I name this. Why is that so? If you look carefully, if I change this to B0, isn't it the same code? Even though it runs in 0, it's the same, right? 8, and now I use 8 here, which is correct because this one depends on this. Okay, this one -1, I change it, I change the B, B, and then I use it here. B equals to C, right? So this one is dependent. So that's why if I change here, I need to change here. But these two actually not affected, right? It's not affecting one another. Right? So right now, because I changed the name, and these two run in parallel now. Can, isn't it? Can they run in parallel? Can, because I'm not writing for right after B anymore, because these are the different variables. They are two independent variables now. And the code is still the same like the previous code. Still. So this is code dependency. So you have to identify, sometimes it looks like it's dependent, actually it's dependent. But if you rename it, then it's not dependent anymore. Then it's still the same code, and you can run in parallel. Only these two statements are you can run in parallel. Okay? Yeah, the same thing for right after right. Okay. This one is a different example. I use different example here. But basically we're talking about the same thing. Okay, fourth dependency as well. Now we're looking at right after right. Okay? The solution is still the same, renaming the affected variable. So that's it. Then I'm going to extend this so that we can better appreciate it. Let's say B is certain value. That's one. Starting from the you can write this way. So you cannot run this in one, you have to change it. Change it, this is affected one. You just change, rename. Okay, you can rename this maybe, you can rename this A0. Then this one must be A0, because this one is dependent. Okay, so you can rename this as well. So down below there, if any code that relates to A0, you have to change it. You have to rename them as well. But before you don't change that, before you don't change it, because you want to show you know. Is this code the same like the previous code? It's the same, right? Right? I write into here, and then I override it, but I can use a different variable. Right now, it's no more dependent. It's just renaming, it's so simple. Right? So luckily it's very simple. And you just need to identify this, and then you can run them. Yeah, of course I gave you a very simple example. In real world, you can identify there are many spots that you look at it, it's dependent. You cannot run them in parallel. And if you do, it will fail. Okay? You just need to change the name. And then magically it becomes independent. Okay? A lot of cases you have this kind of situation where you can actually fix it. Okay? Okay, we don't discuss input devices because of the there's no dependency, just like we didn't discuss. Okay, just now I was talking about the statement that is inside. Okay? Now we want to look at the statement that is across multiple operations. Before we go to that, let's look at another one first. Control dependency. This is not about flow. These are all flow. And right now we want to look at control type. The flow, there's no condition. If you flow from top to bottom, this is also flow from top to bottom. So this is a flow instruction. Then let's look at the control type of instruction. The control type is also has a simple for example, in this case, inside here you see it has if statement. The if statement, if it is true, it will continue. That means it will not cancel if statement.
SPM 那个 slide
哦，
有这样要跟着跟
And then it will continue to the next bit.
没有，
Continue means
是
go
这
to
样
the next bit.
它之前不是说我们
Skipping
怎么
this
restable 的
whatever statement that comes after.
这有什么 restable 过有什么
what is it trying to do there? Actually, it's trying
我
to
跟他，我
divide,
们就是之前讲，好像这个东西写的吧？
and we know that if you divide b with 0, it's
你忘记了？
infinite, right?
看吧。
You shouldn't write. Actually, if you divide, the processor is going to fail. It's going to generate exception, right? So you stop the program. So in order to prevent that, you have to check whether the d is 0. So in this case here, we have control dependency. Because this instruction here, we cannot run this S1, S2 in parallel. Because S2 depends on this condition here. So you need to know the condition is true or false. If it is false, then I cannot run this. If it is true, then I can run. Okay? This is control dependency. It depends on the condition before, whether it should be run or not run. Okay? So control dependency, again, this is a dependency where you cannot fix. Okay? It's unlike force dependency you can fix. This one you cannot fix. Okay, now we want to look at the loop dependency. Dependency in a loop of two different types. One is loop carried dependency. Loop carried dependency is a statement in iteration depending on the statement that is in another iteration. The one that I mentioned to you here. It depends on the statement that is in the previous one or the future. Okay? So that is loop carried dependency. The example is here. You can see in this iteration, it relies on this iteration, but this one, it relies on the previous iteration. Okay? This previous iteration, you will deal with it in the previous iteration, and you use it here. Okay? Previous iteration, you also use, other iteration also you use it. Right? So this one is loop carried dependency. Okay, is in a loop. Then another one is loop independent dependency. Loop independent dependency is what we discussed. It is the dependency inside. Independent dependency is the statement that is dependent on one another. Across the previous one is across. Okay? So what is the rule of thumb when you deal with this problem? How do you know when you should parallelize it? Where can you parallelize it? Okay, all assignment to the shared are loop weights. Okay? And each element is assigned by most one iteration. That means one iteration on it will assign the weight. It's not assigned by multiple iteration. Okay, no iteration with element assigned by another iteration. This is the problem that we see here. Okay? One iteration is read by the other iteration. Okay? So if you see this, that means you cannot parallelize it. But we see later on, we can actually change the case in order to make it not dependent. Okay? So let's have a look at the code. Let's look at the example. Okay, let's look at this example here. This one has loop dependency, loop carried dependency. That means it depends on the statement that is inside the iteration. Okay? So how do we fix this? Firstly is where is the place? The place is here. So I plus 1 is from the previous one. And previously you also update. So you read here. Read in the current loop and write in the previous loop. Okay, because this one is I plus 1, sorry. This one is read from the future. Okay, you read from the future. That means you read the future loop result, and then in the future you write it. Okay, so this is the dependency that you see. Because I plus 1. So you are reading the data from the future, and then in the future you override some of the data. Okay. So how do you fix that? So here is dependency, and you can fix it by doing this. If you do this, then you can run in parallel. Actually, there's a parallel code here. This parallel 4 and this parallel. So right now, this one I cannot run in parallel. I cannot put OMP parallel that you will break. But if I want to run in parallel, I have to write like this. I have to do something to it in order is the same code running. Okay? This one I can run in parallel after I make the change. This one I can. Right? So what do I do there? First, I know that I'm going to read from the future, right? And the future, I'm going to overwrite the value. Why do I say so? Okay, if you look at the code, maybe I'm not sure whether you can see it or not. So I need to show it here maybe. In the first loop, let's put it number there. Let's say B0, C0. I'll give a number so that we can see clearly. Because I'm not sure whether you can see it. So this is the first loop. And then A0, A1 plus X. Okay, this is the first loop. Okay, this is I0. Now, let's look at I number 1. So this is the next loop. The same thing here. I'm going to write 1 plus C1 divided by 2. Okay, A1, A2 plus okay, so I2 is here. Okay, let's look at this two iteration first. Okay, then you can see from there. So this iteration will run first. In the next loop, this one will run with the I equals to 1, right? So this one will run in the next iteration. But let's look at the first iteration. The first iteration, you find this A0, but we are using A1. This A1 is written later. Okay. Isn't that dependent? It actually violates the first Bernstein's condition. Just now I was talking about the Bernstein condition. You already break it, right? Because here you are reading and then you write later. Okay? It's the same problem like what we discussed here. But this one is within the same segment. But this one is across the loop. Okay? So you are writing and you are reading before. Okay? So this is a problem. This is the issue. It break the Bernstein condition. Bernstein says if you have this kind of problem, you cannot run in parallel. Okay? So if you leave it like this, you will not be able to run in parallel. Right? So we need to change it. So how do we change it? Okay, we change it to this. So let's see what we do here. First, we break down into two iterations. So, two different parts of code. The first part of code is this code here. We also run in parallel. This part of code. Run in parallel. Okay? This one code here we break into two parts. And the second one we run in parallel as well. But between these two, we run in sequential. That means you run this one first in parallel. Then when you finish this, then when you run this one. So this part is this first part. This first part. Okay. This is the second part here. Also run in parallel. You can see the partner pointing parallel. Right? Okay. So what do we do here? The first part. If you look at this code here, it is dependent, right? It's dependent. But if you look carefully, you notice that actually it takes the next value, put it into the first. Take the next value, put it in the first. Of course, you also add something there. But we just look at this first. Actually, it copies the next one into the previous one, the next one into the next one into the previous. You can do this part here, then you can run in parallel, and that's what it is doing there. So you put into another variable. I'm not going to call A anymore. So here I got an array called A. Okay, right? But here I'm going to split that into two. I'm going to call A2. I'm going to create a new one. Extra array. And this extra array is A2. So I got A and A2. They are all the same size. to it. I just take this this value here, a plus 1, and then I assign it to a minus 1. That means I move the value. Okay? I move it like that. Okay? I move it to a2. Right? So if I move this value, can I run in parallel? No, right? Because this index 0 can be doing this, index 1 can be doing this, ID 0 of the track can do this, ID 1 can do this. So this one can run in parallel, right? Okay? Now, this is the, if you look carefully here, actually I'm taking this and add to this. Okay? Add with some value, and then I put it inside. But now, what I do is, I move this value up front here. So right now here I have the next value. Okay, I have this next value right now in this equation, which I'm going to use it here. Okay. So if you look at the code down below there, you can see that this a2i is this value here, right? Let's say I is equal to 0. So here is a1, but if I change to a2, let's start in black. A2, 0, plus max. Previously, this is 1, right? 1 is here. But because I move this to here, so it's in 0, right? See that? Right? So when I do this, basically this 2 is the same, isn't it? Because I already moved this one to A2 0. Okay? But different name. See this different name there? Okay? And in the future, I'm going to override it, but it's fine because I'm using my own copy. So this is something similar like renaming as well. Because I rename it. Except that now, my renaming is the whole array, not only one element. Okay? Here I'm looking at the array of renaming. So here A0, A20, and A1, A21. So I rename it and I copy the data up front in the first place. And then here when I compute it, I will be using this value, and this value is the future value, and which I'm going to override, but I'm not going to override A2. So right now they can run in parallel. These two can run in parallel because they're not independent of one another. Why? Because I break the problem. Just now, this one and this one is a problem. According to the baseline, we cannot run in parallel. Why? Because this is right after read. Right? But right now, if I change the code here, is it right after read anymore? No, because this A2, this A1 is no more. So I break it. So basically, it's the same as what I was talking about here, except that this one is not across the. This one is across the. Okay? So I can run this in parallel. I also can run this in parallel. Because I already break the problem, the condition where this is before is right after read. And right now there's no right after read because I renamed that. Okay, so what is the disadvantage of this solution? The disadvantage is because when I rename, I have to create a new variable. Here I rename, I have to create two variables, B, B0. Here also the same thing. Here is even worse. Because I got array, so I have to create the whole new array A2. So you have I have 1,000 bytes there. Okay. Then I have to create an additional 1,000 bytes in order to run in parallel. Is that clear? Okay, so this is a false dependency as well, but across the okay. Okay, the next part I think is more or less the same. But this one is actually across the different array. Okay, this how to solve this actually. actually is we don't have to use two different kind of array. We use the same array, we just shift it over. Okay, the diagram is like this. Initially, you can see in this loop here, okay, if you look at the instruction, C I is placed into, added into AI, which is this one. Okay, so this instruction that you see here is basically this. Okay, and then the first instruction is A minus 1, and then you add it into BI. So this data actually comes from the previous iteration. Okay, it comes from the previous iteration, and you use here. So in order to fix it, you just need to shift this. This B, shift it to the right. So you will shift it to the left. So when you shift it to the left, it looks like this. Of course, it's a bit confusing, but maybe I can need to draw it. Let's draw this. I've got this. And I've got this. Okay. So in this iteration, you see there's arrow there, right? The arrow means it's dependent. So this one is used here, and this one is used here. Okay? Okay, maybe I should draw number there. This is 1, this is 1. That means this is the same iteration. Okay? Now, if you look here, this one, this second iteration, 2, actually is like this as well. Okay? Now, if I were to, of course, this one also the same. This. Okay? Now you can see that this one is straight, right? But this one is slanted. So what you need to do is you have to move this one to the left, one step. Okay? If you move to the left, then this one will be straight, isn't it? So it will look like this. So this is 1. Okay. And just now, because I already moved to this side, right? So right now it becomes like this. Because here was something like that. So right now this also is the same, but here is 2. Now this is 2. Okay. Because I shift this to the left, so basically this one becomes like this. So right now, if you look at one of these, actually they are dependent on one another within the loop. It's not from the other cycle. Okay, so you just need to shift it. Okay, but when you do the shifting, you have to change the code. Okay. So after you shift, right? If you look at the code there, B is actually initialized to some value, right? So you have to move that extra out. You cannot do inside there because you shift it. Because when you shift, the first part is not done. So you have to do it separately and outside. Okay, that is the first part because you miss that. Okay, because once you shift, you have to do this independently outside before. Only one time. Okay, and the last one as well. Yeah. So you have to deal with this and this because when you shift, you have to do a special case for this, a special case for this. Because all this is in the loop, right? So this is the extra one. So you have to deal with one side. Because one is outside there, the last one is down below there. Okay? So this one is for the statement 1, this one is for the statement 2. Okay? But if you expand it out, it's still the same, huh? You do the B first, then you do the A. You do the B and then you do the A. If you look at the original code, it's the same thing. You do the B first, then you do the A. You know? So basically is you expand this out again, and then you move this one out. Okay? And then you move the rest up a little bit. So that is what it is doing here. Okay, so that the dependency is not coming from the previous iteration or the future iteration. In this case, it is from the previous iteration. So if you shift slightly, then you fix the problem. Okay, so that right now the you can assign. Okay, in this case here, you cannot assign. Okay, if we assign ID, okay, let's say ID 0 to do this, ID 1 to do this, that means this is the thread, right? ID 2. Why this one will not work? Because this one okay, but this one rely on the previous data, right? So this rely on this one rely on this. So they are dependent on one another. You cannot run them parallel. But if you do it this way, then it's okay. Because ID, let's say this ID 1, this ID 0, this ID 2. Okay, they are not dependent on the previous iteration, and the previous iteration is done by ID 0. So ID 0 use this data, so it's not dependent on other iteration as well. So it can run without any dependency. Here also it can run without dependency. Here also cannot run without dependency. Just by shifting this to the left. Okay? So if you draw this diagram, you can actually see it clearly. Right? So if let's say you've got a problem like this, they are dependent on one another, you check whether you can adjust it. Okay? If you can adjust it, you adjust it so that you can run in parallel. So right now you can run in parallel if you do it this way. But initially you can't. Okay? I think it's a bit hard to see, but if you go back, you slowly check, look at it, I think you can understand what I'm talking about. Huh? Still cannot. You have to pay more close attention to it. Okay, because I have no time to understand. But you can ask me later on, if let's say you still have a problem understanding. Okay. Just want to talk about first time condition on parallelism. Actually, here doing the same thing again. It basically means just now is in theory. Right now we want to look into the practical use of it. Okay. The first condition was we are reading from one iteration or the first statement, and then that same variable you're writing it. Okay, so you must make sure that that does not happen. So the input set, you got statement 1 and statement 2. Okay, in statement 1 you are reading, in statement 2 you are writing, and make sure that you are not writing into the same variable. Okay, so here is the set. Maybe I'll show it to you here better. Obviously easy to see. Let's look at this example. Okay, I have instruction 1, statement 1. Again, use instruction. Actually, we have to S to it. In this instruction, we have this equation. Okay. And then in second instruction or the second statement, we have this instruction. Okay. In the third one, we have this instruction. X2 plus A multiplied by P and so on. Okay. So what we want to check is whether you violate the first condition of the sign, second condition, and third condition. So this one is read in the first statement, write in the second statement. This one read in the second statement, write in the first statement. This one write in the first statement, write in the second statement. Okay, we want to make sure that there is no variable that write in the same variable is used by both statements. Okay, so that is the reason why we put it in conflict. In order to find out, because when it becomes complex like this, it's easier to actually put it into the set. Okay, because there are so many variables that you know. We can check one by one, just eyeballing it, but it's better to use this set in order to find it. Okay, so let's look at the read set and write set. Okay, so the read set set for read 1 here means instruction 1. We want to find in the set here what are the variables that we read. Okay, we are reading from A, we are also reading from B, so A, B. Okay. How about write? Do we write into anything? Yes, we write into X. So we write X. We don't write into A, we don't write into B. Okay, so that's the first thing. How about the second one? R2. We read from B, we read from C, we read from D. And we write into Y. Okay? And how about this? Z is we write into Z, so 3. Yeah. And we are reading from X2. Read from X2, A, and E.
我才完全那么高。
It's actually X2 means 2 times X. 2 times X. That's why I think there's a mistake. It should be 2 times X. Okay, so you're reading X, you're reading A, you're reading E. Okay? And you're writing into Z. So that's what we get here. Right? So the question right now is to ask this. I want to see if between these two conditions here, sorry, these two statements here, instruction 1 and instruction 2, or statement 1 and statement 2, between these two, whether I violate this Bernstein condition. So the Bernstein condition for the first one, it says this, R1, okay, and with this 2, it needs to be, the set must be empty. Okay, it should be empty. Right? So that's the first condition. So let's see whether it satisfies it. Inside here, is there any same variable? No same variable, right? So it is correct. It's true. Because none of them satisfy. Okay? And the second one, for this same instruction, we look at it. Here we write and we read later on. Okay? So let's have a look at just now I was looking at the wrong one. I should be looking at these two just now. So A, B, and Y. So it's not. Now I'm looking at these two. Okay? So B, C, D, and X. Okay, B, C, D, X. So it's also no, so it's true. Okay? How about the third one? The third one is right. Right. Okay, we check whether it's true or not. Is it true? So let's have a look here. You write and then you write, which is true. Okay, so these two you can run in parallel. You can run in parallel. Okay, so let's look at these two. Want to see whether it can run in parallel. Okay, we have to check one by one. So if this possible to run in parallel. In order to do that, we have to check again. But this time it's going to be the first one is going to be R2 W3. Okay? And then the second condition will be W2 R3. Okay, the third one will be W2 W3. Okay, so check this out. So R2 is this one. W3 is this one. So you check. Is there any similarities there? No, there's none that is a separate specific. So here is now set. Okay, how about this? This one is W2 and R3. These two. This one was these two, and now these two. You see that it does not contain any set that is similar to that. So it's null as well. Okay? Now how about W2 and W3? These two. Also null. Okay, so you can run this in parallel. These two in parallel. Okay? So let's look at the last condition. So we know that this one can run in parallel. These two also can run in parallel. Now we have to check this two. This one and this one. Whether it can run in parallel. Because if all of them satisfy, that means these three can run in parallel. All of them can run in parallel. So let's check. First one is R1 W3. W3, right? So let's check that. Second one is W. So this one is W1 R3. Third one is W1 W3. Okay. So R1 is this. W3 is this. Okay, there's no set that is the same, so it's no. Okay. How about W1 R3? Now we got problem there. Because this one is there. So you got X here. Okay? X. AE is not there, but X is there. Okay, actually you don't have to check anymore, but let's have a look at this. This one and this one is not, so it's no. But because this one failed, right? This one is okay, this one okay, but this one failed. That means these two cannot run in parallel. Okay? So, can you run in parallel? This three? No. You cannot run in parallel. But you can choose this. You can run this in parallel. But this one must be run in sequential. These two can run in parallel, but these two sets must run in sequential. Okay? Or you can do like this. These two can run in parallel, but these two sets needs to run in serial. Run this one first, run this in parallel. You understand? Okay, so Bernstein gives us a way to actually to more systematically find out whether we can run that in parallel. Okay, using this this set, because this set is going to give us a better way to see this condition. Okay, if let's say you're writing and reading the set that provided this, you know that you cannot run in parallel. As long as one of them fails, you don't have to check the rest of it. So for example here, if I check this, okay, this one not okay, I don't have to check this one, because it will not be able to run in parallel. Because either one fail, you don't have to check anything. Okay? But if in the exam they ask you to write down all, you have to write down all, and you cannot just skip this one. Okay? But for practical use, of course, you can see. In the exam, if they ask you, please don't skip it, you have to write all answers. Okay, so that is this part here. Okay, let's move on to the next one. Okay, I have only a few minutes. I'll just go through a little bit. I think this part is not so easy. This is just a continuation of what we have discussed. First, we want to look at this is kind of algorithm we have already seen many times. We'll just go through this again. And the model of parallel algorithms, what kind of model that we have, I think we also discussed this already. We will try to look at some example. And then we analyze the sequential algorithm and analyze the parallel algorithm, and then we look at the Amdahl's law and Gustafsson law. I think Gustafsson law is missed. Actually, when we do this Gustafsson law, what are these laws? Okay, it's something to do with the limit of parallelism. So the parallel computing, the goal, of course, you know already, is to make sure that you run them in parallel, able to run them in parallel. And of course, it can run in parallel those that have strong scaling type of problem, where you don't have dependency. Okay, some of the problem you cannot scale. Okay, it is weak in scaling. You cannot solve that easily. Okay, so you have to use different ways in order to find the solution. Sometimes it's kind of misleading if you don't analyze it. Once you analyze it, you can check whether it is able to be run in parallel. Okay? Because we use the parallel computing in order to run our computation faster, especially those that requires fast computation. Let's say AI, you don't want to wait forever in order to get an answer, right? You want AI to answer you immediately. So AI requires parallel computing. We all know that AI use GPU, that's why GPU price is very expensive. Okay, another things that we have to look into is data sharing. Because once we have data sharing, it will prevent us from doing parallel computing. But of course, if we know how to actually adjust the data, we're able to make sure that they don't share and then race with one another, we can run them in parallel. Here we have a lot of synchronization that we learned before, synchronization using the text bindings and all that. And also we can make the thread wait for one another to ensure that they run in certain order. Okay? Of course, barrier is bad. If you have to wait, that means you are making your parallel computing slow. Okay? So try not to use synchronization if it is not necessary, don't use. Don't use barrier because it makes them wait and parallel computing will suffocate. Okay, so here it says waiting is loss of efficiency. That means it makes your program run slow. Anything that involves synchronization, if you need to use it, you use it. But if you don't need it, please don't use it. Because if you use it, it's going to slow down the system. Okay, we have many different kind of algorithm models to allow us to run them in parallel. Okay? So we can organize by task, we can organize by data. Organize by task is basically functional decomposition. Organized by data means you organize by decompose by domain. Okay? And also one thing that we did not discuss earlier on is the organized by data flow. Okay? That means how the data is consumed, whether it is pipeline or even driven. That means you don't look for the data if let's say you do not need it. When you need it, then only you get it. So that is data flow. Data flow means you don't run according to the program, you run according to the flow of your data. Your data comes, then only you run. If you don't have data, you don't run. Okay? So you can have this kind of different algorithm structure to run them in parallel. So I think this one is quite new, we never discussed, we only discussed the first two. Okay? This one is also important, and this one is emerging, especially big data, especially IoT. IoT has this event driven. That means the data only comes when there is some kind of event. Okay, the decomposition we discussed many times, so I'm going to skip that. Okay, this is an example of multiplying matrix with a vector. So you have matrix with a vector, we can run this in parallel. For example, task 1, focus on row 0, and row 0 is independent of row 1. Right? We should call it task number 2. So task number 2 here, if you run, you can run in parallel with task number 1. The same thing, task number 3 is wrong. Why? Because they don't rely on each other's data. Although they share B, and B is shared, but B is not changing. Okay? So B is constant. In this case here, it doesn't change. So it can run in parallel. Okay? So this task 1 can find this solution 1, index 0, until index M. Okay, they can run in parallel. So you got N thread, all of them can run in one go. So the observation that we see here, this one is a massive parallelism available for us to solve this problem. Okay? Let's look at some example that is not typically matrix, because normally we use matrix to solve it.
Let's look at a problem where I think the wire is not properly, that's why you cannot hear my voice. I can hear it. Okay, this one is dealing with database. Okay, so database has multiple information there in the database, right? So you have ID, which is the ID of the car, and the model of the car, and year where it was produced, the color, the dealer that you buy from, and this is the price. Okay, let's say for example, if I want to find from this this database, I want to find a model where it is a Civic car, the model series is Civic, and then the year produced was 2001, and the color is either green or white. Okay? If, of course, this table is quite small, but imagine that you've got billions of information inside there. Can we run that in parallel? Of course, here we know matrix we can, but let's look at this example, new example here. We can solve them in parallel. We can break them into this. We can break them into different way, but let's look at the first example. We can look at these two, this one, and this one as two different problems. Okay? So we can ask track number 1 to look for this information, and then track number 2 look for this information. Okay? And they can run in parallel. Okay? Because if you look at this, they are not dependent on one another, right? So they can run in parallel. So the first one, we are looking for a Civic car, and then you're looking for the year. So within this itself, you can also break it. You can break it into one track here, another track there. Okay? And here also you can break it into two different parts. One track here, one track here. So you got 4 tracks. The first track is to check whether the model is Civic, list all of them. The second, look at the year. The third track, look at the color, green. The fourth one, look at the color, white. Okay, so this is how it looks like. So first, the track will look at the ID, look at the database, and check for the car that is Civic. So it produced this. Zoom in further, so that it's clearer. Okay, so Civic. So if you look at the Civic car, all of this Civic, 1, 2, 3, 4. So there are 4 there. So first track will find all the Civic. But even though it's not true that you're going to use all of them, it's fine. You just produce this result in a table, Civic. Okay? The second one, you look at the year. So the year 2001 is this. Even though it failed, for example, this one is Camry, Prius, Altima, but it doesn't care. It just look at the year only. So it identify the year and then bring out the car ID. Okay? And the third one, look for the white car. And the fourth one, look for the green car. So green car and the white car is this list. Okay? So this one is run in parallel, and they come up with this table in parallel. Okay? With this table, we can move on to the next stage. The next stage, we look at the query again. The query says Civic and year. So we use these two results run by one thread. So this one is 2 threads, right now reduced to 1 thread. So this 1 thread is using this smaller table. Just now you look at the bigger table, now you look at the smaller table. Now this table here, you check for Civic and 2001. So which are the one that is matching? The first one failed, the second one yes, Civic and year 2001. The third one yes, Civic and this one, and the last one it failed. So the second and the third one actually passed, so it gets filtered out. Okay, so you got this ID, Civic 2001. Okay, what about here? First you check for the ID that is similar, and they have the same color. So, sorry, this is all, right? So you just mix them together. You don't have to add. Here is and, here is all. Or you just add them together. So when you add them together, you got 4 here, 2 here. So you got 6 altogether. 4 plus 2, 6. Okay? So once you finish that, now the last stage, use one thread to compute it. Okay, so it looks for the ID which is matching. Which are the IDs that's matching? This one, which is white.
可是你帮我问一
Okay,
下
and then the
他，
next one
我们有一点点
is
差别是 OK 的吗？因为
there's only one,
因为
which is what
那个叫
color.
什么
So we found
我
it.
上网 check 啊，
Okay, so
他是讲
the
因为
last thread
GPU 是
actually
用做的
found
关
the
系跟
solution.
CPU 有差
And
别
you go through how many stages? The first stage,
啊，他是
the
讲有差
second
别，
stage, the last stage. In the first stage,
所以
we can run
问看他
4
OK
threads
没有？我是
in parallel. In second stage, you run 2 threads in parallel. The last stage, you run 1. Actually, Google use this kind of technique to find your search very quickly. Okay, so you got different parameters, right? So you pass into multiple processor, and this processor will look for it, create this small database, then you move on to the next stage. The next process will, because it has smaller database, so you can find quickly. And when you reach the last part here, this last part actually use a smaller table in order to look for the solution, and then you give it to you. Okay, so this how majority of parallel computing in distributed manner is done. Okay, apart from just what we have seen before using matrix. Okay, just now I showed to you that we can decompose it by doing that way. We compose this and then we combine them one by one. Another way to decompose is this way. Sorry, I think it's over already, right? Okay, I just showed to you here. First is 3, and then you combine this, and then you combine this with the year, and then finally you combine with the city. So there are many ways to actually solve the problem. Okay? Yeah, I'll discuss this next week. This is a guide. Okay, you only explain the code when it is necessary in the assignment. Okay, you don't have to explain the code because I want you to explain at conceptual level rather than the code concept. Okay, at the conceptual level, what and how you don't explain line by line because it's going to be lengthy. You don't have enough space to.
我做完了，然后我还要加点。